All right, so here's number 4 for assignment 4.6. It says find the intercepts. You never know who's going to end up behind my shoulder here. That's okay. Find the intercepts, extrema, points of inflection, and then graph. So we have f at x equals x cubed subtract 3x. We're going to do all kinds of analysis, then graph it without a calculator. So if I want to find the intercepts, I'm going to factor out, an x, and I have x squared subtract 3. And then if I take the first factor, x, 0 is an x-intercept. If I take the second one and make it equal to 0, take the square, the answer is positive and negative root 3. So those are my x-intercepts. And I'll approximate where root 3 is when we get there, and negative root 3. Now, also, it's good to know they're all odd, just to let you know. Even if it has an x squared, it's really x plus root 3, x minus root 3. If you write it as a linear, so as a quadratic, it doesn't really count in terms of when we look at the multiplicity. So these are all odd. They're going to cross at each one. The y-intercept, if I plug in 0, the answer is 0. So I've covered the algebra part. Now, if I take the derivative, if I make that equal to 0, and then if I solve it, I get positive and, there you go, positive and negative 1. If I draw a number line for the first derivative for negative 1 and positive 1, I have my intervals. So into the derivative I go. If I plug in a negative number smaller than negative 1, the answer is going to be positive. If I plug in a number between negative 1 and 1, it'll be negative. If I plug in a number bigger than 1, it's going to be positive. So at negative 1 creates a maximum. And then I plug negative 1 back into the function to find the y coordinates. So that'd be negative 1 plus 3, that'd be 2. At positive 1, as it decreases and then increases, creates a minimum. And then again, plug here and you get 1 take away 3. So at 1 negative 2 is a minimum, a relative minimum. So we have two turning points. This is called your extrema right here. Take the derivative one more time and you get 6x. Make that equal to 0 and solve it. 0 is the only one on our number line for second derivative, for concavity. So if I plug a negative number into here, it's going to be negative. If I plug a positive one, it's going to be positive. So I have a point of inflection at 0, 0. So not only is it an x and y intercept, it's also a point of inflection. All right, now I can graph it. Get up to 2 and down to negative 2. All right, so here's a great example of just a real basic polynomial where you do algebra and calculus to be able to analyze and graph it. All right, so we have 0, 0. We have root 3, which is pretty close to 2. Negative root 3, which is pretty close to negative 2. What else do we have? We have a relative max at negative 1 and positive 2. And then a relative minimum at 1 and negative 2. So there's my turning points. I knew from the beginning my end behavior, the right end goes up and my left end goes down because it's positive x cubed. Put it all together and you have a beautiful looking graph without using a calculator. So you're able to find the intercepts, the turning points, and concavity. So I also knew that right here it goes from concave down to concave up, and 0 is a point of inflection as well. Man, it all came together. Very pretty. Number 5. And number 5 says, without using a calculator, graph g at x, x cubed subtract 3x. Now we just did this graph here, so I'm going to come back here. So if you're going to do the absolute value part, whatever is underneath, it's just going to be reflected up. So this part is going to be reflected up. And here, this turning point will turn into 1, 2 over on the other side. So if I was going to graph the absolute value, so nothing will be below the x-axis. Everything is positive in the y's. We have our 0, 0. We have 1, 2. We have our intercepts. Those intercepts are the same. And so this is what it would look like. So what was below is above. All right, so there's just a reflection. So any part that was here below got reflected up, and then you draw it. All right, number 6. It says, find the maximum and minimum points on the graph that. So in order to find the maximum and minimum points, we need to take the derivative of that. So we have 9x squared plus 4y squared. Subtract 54x plus 8y plus 49. And so we're going to do this implicitly. So that's 18x. That's 8y, but it needs a y prime. Negative 54. 8, but it needs a y prime. And then the derivative of 49 is 0. So if it has a y prime, it's going to stay. Otherwise, we're going to subtract 18x and add 54. We're going to factor out y prime to get y prime by itself. And then the last step is to divide. Now, to find the extremes of this graph, you have to make it equal to 0. And if I make this equal to 0, it's just the numerator that needs to be 0. So we're just going to take only the numerator equal to 0, because if the numerator is 0, 0 divided by anything is going to be 0. I'm going to solve it, so I'm going to subtract 54 to the other side and divide. So I get the answer 3. And now I want to find what that is. So this is going to be one of the extreme x values, but I need to find the y coordinate that goes with it. So, oops, I'm going to make sure where there's an x, can I write this properly? 9x is 3. So instead of 9x squared, it's 9 squared. 4y squared minus 54 times 3 plus 8y plus 49 equals 0. All right, so I'm going to simplify this and solve it. So this is 9 times 9, that's 81. This is 54 times 3, which is what, 150, 162. Y. Here we go. 81 and 49 and negative 162. They combine to negative 32. So I have 4y squared plus 8y minus 32. That's what the constants simplify to. I'm going to divide everything by 4. And then I'm going to factor. So it's positive 4 and negative 2. So I get the answer for the y coordinate to be negative. So if we factor this, it's positive 4 and negative 2. If you solve it, it becomes negative 4 and positive 2. So we have, this creates a minimum. So that means we use the same x coordinate. So we found 3. So 3, negative 4 is the minimum. And then this here, 2, becomes the maximum. So this is the minimum point. Actually, they're not even relative. So they didn't even say that. So just the minimum point and the maximum point. So this creates a minimum point at 3, negative 4. This creates a maximum point at 3, 2. And this is minimum because of the y value. This is maximum because of the y value. All right, number 7. It says find the absolute extrema. So absolute means I need to do a table of values. So I'm going to do that right away. And the ends are -2 and 3. So before I forget, I put the ends right in right away. To find the other critical numbers, we need to take the derivative. So 3 times -1/3 is -1x squared plus 1. That's the derivative. Make it equal to 0. So we're going to add x squared, take the square root. So it's positive and -1. So I need to make sure I add +1 and -1. And notice +1 and -1 are both in my domain restriction. So I had to make sure that +1 and -1 are within -2 and 3. So if these numbers were not in the correct domain, then I cross them out and only use the ones that are in the domain. But they all are. So I have 4 that I need to plug in. So again, the function itself was -1/3 x cubed plus x. So each one you're going to plug into here and get a value. So for -2, it's 2/3. For +3, it's -6. For +1, you get +2/3. And then for 3, you get -6. So try to get 3 gives you -6. Sorry, -1 gives you -2/3. +1 gives you +2/3. -2 gives you +2/3. So if I'm asking for the absolute max, then that would be +2/3. If I'm asking for the absolute minimum, I'm looking for the y value. That's the smallest, which is -6. So it's not a point. So once you do your table of values, plug into here to get these y values, and then the largest y value is your maximum, and the smallest y value is your minimum. All right, number 8. Again, it says find the absolute extrema on an interval. So I'm going to again do a table of values to remind myself. This one is G, so make sure I have the right letter. So for this one, again, the interval goes from -8 to 1. So I'll make sure that is on my table of values. You have to include the ends of the interval. Then the derivative. So let me make sure I'm going to write g of x right away. So 3/2 x to the 2/3 subtract x. The derivative here, if you'd multiply it, it would just be x, because 2/3 times 3/2, they cross out, leave you with 1. Subtract 1. So 2 take away 3 would be -1/3. Subtract 1. Now, because of the negative exponent, I already know 0 is 1 because 0 makes it undefined. So this is like 1 over the cube root of x minus 1. So because it's in the denominator, what makes this undefined, 0 is one of the values. The other thing that would work here is, if you make it equal to 0, is that 1 to any exponent is equal to 1. So 1 take away 1 is 0. So the other value would be 1, but 1's already on there. The other one is 0, which is already there. So 0 is there because it makes the derivative undefined. If I solve it, the answer would be +1, because 1 to any exponent is 1, and 1 take away 1 is 0. So these are the only numbers to test for absolute max and min. Put them back into here to be able to get the values. So if I plug in -8, this is squaring, this is cube rooting. So if I cube -8, it's -2. But if I square it, it's 4, and 4 divided by 2 is 2. 2 times 3 is 6. 6 take away 8. I get -2. 14? Yeah, negative, right? So 6 take away -8, so +8. That gives you +14. If I plug in +1, 1 to any exponent is 1, so it's 3/2, take away 1, which leaves you with 1/2. And then plug in 0, and you get 0. So from that, you will get your minimum and your maximum. So your lowest y value there is 0, and your greatest y value there is 14. So between that interval of -8 to 1, the greatest y value is 14, and the smallest y value is 0. What number is that? Number 9. In number 9, it says, can the mean value theorem be applied? If, and so on, find it if it is, and so on. So we have 1 over x squared from -1 to 2. Does the mean value theorem apply? This is when I rock equals A rock. Two conditions. Is it continuous, and is it differentiable? So in this situation, you can see that x can't equal 0, and that number is in my interval. So because it's not continuous at 0, the MVP does not apply. So it has to do with continuity or differentiability. So it has to do with that it's not continuous at 0, and that is in my interval, so the MVT does not apply. Number 10. So for this one, you can see that x can't equal positive 3, because that would make it 0 in the denominator. But 3 is not in my interval. So from 4 to 6, it's okay. And from 4 to 6, it's also differentiable. So for this one, it actually does apply, and it will work because of the interval. Now, I need to do the I rock and the A rock. Let's do the A rock first. That's f at 6, subtract f at 4, divided by 6, subtract 4. That's the difference quotient, or the slope formula. Plug in 6, and you get 6 divided by 3, which is 3. Plug in 4, and you get 4 divided by 1, which is 4. And so I get negative a half. Sure I'm on the right track. Try that again. So 6 take away 3 is 3. So 6 divided by 3 is 2. So this actually is negative 2 divided by 2, which is negative 1. Now we're on track. And then take the derivative. So if I would take the derivative here, I need the quotient rule, which is the bottom, times the derivative of the top, which I don't need, minus the top times the derivative of the bottom, and then the bottom squared. So there's the derivative. I'm going to make that equal to negative 1, and I'm going to solve it. So on this side, I have x times minus 3 times 1 minus x. I can totally simplify that. I'm going to multiply both sides by x minus 3 squared. So if I multiply by x minus 3 squared to both sides, then I have negative 3 equaling this. Now, if I FOIL this out, in fact, I don't even need to FOIL it out. So both sides are negative. Just solve it the way it looks. So divide both sides by negative 1. You have positive 3. Take the square root of both sides, and you'd have positive and negative root 3, equaling x subtract 3. Add 3 to the other side. And these are your two answers. Now you have 3 plus root 3, or 3 take away root 3. So 3 plus root 3 or 3 take away root 3. Go back to my interval. In fact, I'll write it here. The interval was from 4 to 6. So the interval was from 4 to 6. So this one is not right, because that number is not between 4 and 6. You're going 3 take away something. So 3 plus root 3 is in that interval. So when C equals 3 plus root 3, I rock equals A rock. So that mean value theorem says that the average rate of change has to equal the instantaneous rate of change, at least at one x value, maybe more. In this case, there's only one, and it's exactly at 3 plus root 3. All right, number 11. One more of those A rock equals I rock. So in number 11, you have f at x equals x minus 3 plus 2 from 2 to 5. Now, one thing I recognize, it's absolute value. So it's a v. That means there's at the vertex is not differentiable. So where's the vertex when it's in this? This is called HK form, transformational form. The vertex is at positive 3 and 2. So at x equals 3, it is not differentiable. It is continuous, but is not differentiable because of its sharp corner. And because it's not differentiable at 3, and 3 is in the middle of the interval, the MVT does not apply. So absolute value, you know the shape of it of a V. At the vertex, it's not differentiable. And the vertex happens to be in the middle of the interval, so the MVT does not apply. So the two conditions again for the mean value theorem is it continuous and is it differentiable in the interval given? Then IROC equals AROC at least one x value, and then we show that. All right, given a bunch of information, I'll write it down. F at 4 is 2, G at 4 equals 3. The derivative at 4 equals -1. The derivative at 3 equals -2. And the derivative at 4 equals 5. So here's a great kind of AP type of question when they give you all kinds of different values. And then for A, it says h at x equals f at x times g at x. So totally AP style question here. Given value, can you do the rule? So the rule here is the product rule. So take the derivative. So that's the first times the derivative of the second plus the second times the derivative of the first. So do you know the rule? Then you plug in 4 and then look above and plug in the numbers. So plug in 4 for x and then look to see what values you're going to use. You're not going to use them all. So f at 4 is 2. G prime at 4 is 5. G at 4 was 3, and f prime at 4 is -1. So 10 take away 3, and you get your answer 7. All right, put down part B. Recognize what rule it is, and then apply the rule generically. So for part B, I have the answer key off here on the side. I want to make sure and double check I'm doing it right and I'm not lying to you when I do the work. Here we have J. You don't hear CJ as much. And you have f at x all cubed. So if I want to take the derivative here, this is called the chain rule. So 3 times 1 in front, and then times the derivative on the outside times the derivative on the inside. Then it asks you to plug in 4. And then that's it. So then you look for the values for it. So f at 4 is 2. And then f prime at 4 is -1. So f at 4 was 2. F prime at 4 was -1. So this is 12 times -1, so I get -12. Part C. In part C, k at x equals f at g at x. And so take the derivative. This again is the chain rule. So it's the derivative of the outside times the derivative of the inside, and then plug in the value 4, and then go back and find what the values are of those things. So g at 4 is 3. G prime at 4 is 5. And then you have to do it one more time. So you found the inside part is 3, but now you need to take the derivative at 3. So f prime at 3 is -2. So it's -2 times 5, and I get -10. Just to make sure that I did it right. I don't even see it on my answer here, but I believe it's right. And you got it. All right, number 13. In number 13, another great AP style like question. You have piecewise. And you're asked about continuity. So find A and B, so this is continuous. So the limit as x approaches 2 from the left has to equal the limit as x approaches 2 from the right. So in this case, in that situation, 2 from the left would be the above one, and you'd plug in 2 for x. And then 2 from the right would be the middle one. And again, you'd plug in 2 for x. And now you have an equation. So I have 4 plus a, 2 minus b. I'm just going to clean this up a bit. So I'm going to add b and subtract 4. So now I have an equation to work with. The other part that would make it continuous is that the limit as x approaches 3 from the left equals the limit as x approaches 3 from the right. Oh, it would also have to equal this. That's the definition of continuity. So the value of the function and the limit as it approaches left, the limit as it approaches from the right, if all of these are the same answer, it's continuous. Same thing here. The limit as x approaches from the left, the limit as x approaches 3 from the right, and the function value, if they all are the same value, that's a calculus definition of continuity. So in the middle, again, this time I'm going to plug in 3, and then in the bottom I'm going to plug in 3 for x, and then I'm going to solve it. So we have 3 subtract b, 9 take away 1 is 8. I'm going to add b and subtract 8, so b is equal to negative 5. If that's true, then a, so if b is negative 5, that would mean a would have to equal 3. Done. Good job. All right, turn the page. Number 14. Number 14, we have some limit questions. So the limit as x approaches 3 of x subtract 3 over x squared minus 9. Step 1 is to do a substitution. If I plug in 3, it is indeterminate. Do not write down equals 0 over 0, but it is indeterminate. So because it's indeterminate, I look to factor and remove. So likely something is removable. So if I factor the denominator, I can see that x subtract 3 removes. Now when I plug in 3, I get 1 over 6, and I have my answer. That was part A. Part B, the limit as x approaches 3. And this was x plus 3 over x squared minus 9. So it almost looks like the same question. But if I substitute 3 into here, I get 6 over 0. That's different than 0 over 0. See, 0 over 0 is indeterminate. That means I can factor and go further. 6 over 0 is undefined and the limit does not exist. Done. So there is a difference between 0 divided by 0 and any other number other than 0 divided by 0. So 6 divided by 0, that's undefined. 0 divided by 0 is indeterminate, and you could perhaps factor and remove and keep going. Part C. This is limit as x approaches infinity. This is an n behavior question, and we're going to look at the power on top and the power on the bottom. So if I look at the power, on top divided by the power underneath, so it's power term divided by power term, the right end behavior is 3 over 2. Part D, the limit as, again, x approaches infinity, so again the right end behavior, and I have 3x cubed plus x subtract 3. This time I have 2x to the 5th subtract 9. So again, this is the right end behavior. Where's the ends going? Look at the power terms. So if I have power divided by power, whenever the bottom is more powerful, the ends are going to 0. If they have the same power, we divide in whatever the number is. If the numerator is more powerful, I divide, and what's left over, I look at the end behavior of that. So if it's x squared or x cubed or x to the 5th, I would look at what's left over after you divide the power terms. But in part D, if the denominator is more powerful, the ends are going to 0. All right, number 15, 16, and 17. It says use these graphs of the derivative to graph the second derivative. So first of all, let me just look off of here and then see what information I get off of this. So for the first derivative, I'm looking, if I want to graph the second derivative, I'm looking at increasing and decreasing. So the first part is increasing, then it is decreasing, and then at 0, it's undefined. So if I want to graph number 15, that's the first thing I look at. It's increasing, then it's decreasing, and then it's undefined as a curve. So if I come here, so if I did a second derivative number line, 0 is a critical number because it's undefined. And I said it's increasing and then decreasing. So if I did a sketch of that, at 0 it's undefined. This is still increasing, and it's above. And the second part is decreasing because it's below. So above and below, that's what I'm looking at. And at 0 is the asymptote. I know it's a challenge. We're going to try the next one. So at number 16, what are the things I'm looking at in number 16? So if you did a second derivative number line, I'm looking at increasing and decreasing. So first of all, it goes from -2 to 5. I see at 2, we have a critical number. And then after that, what else am I looking at? Increasing and decreasing. So from -2 to +2, it's increasing. And from 2 to 4, it's increasing with a constant number. So what is that constant number then? It's the slope up 1 over 1. So this is one where the slope is equal to 1. It's going to be a horizontal line. While the other one, so at 2, there's going to be a hole. And the slope is 1. So that goes to 5. 3, 4, 5. So here to 5, it has a slope of 1. And then on the other side, it's increasing, so it's above. Interesting, at -2, you have a vertical tangent. So at -2, you have a vertical tangent, which makes it undefined at -2. So it's going to kind of look like this, where it has that, at first, it is rapidly increasing, and then it kind of flattens out a bit, and then the horizontal line. These are challenging questions to be able to graph the derivative of a derivative. 17 will be a little bit more basic. So in number 17, what I'm looking for are the turning points in increasing and decreasing. So I see -2 as a turning point, I see 0 as a turning point, and I see +2 as a turning point, and then increasing and decreasing. So first of all, it decreases, increases, decreases, increases. So you have a sense of above and below. Now all these turning points are x-intercepts. So at -2 is an x-intercept, at 0 and at 2 again. Those are intercepts. And then it's going to be below and then above. So it's below and then above, below and then above, and then you've done it. So below, above, done. Number 18. All right, horizontal lines are easy. So the slope of a horizontal line, so all I see is at 0, it's undefined. That's the only critical number. And then the slopes are 0 and 0 on both sides. I'm just looking at the slope. So the slope on both sides are 0. Not whether it's above or below, just the slope. Is it increasing or decreasing? It's neither. It's just the slope, and the slope is constant for both. So this will just be a graph where at 0, there's a hole, and then to the right and to the left, it's right on the axes. That's it. So it's there. This represents the slope of the slope. So when I look off the graph, I see the slope is 0 on both sides. That's what I'm looking at. So here represents the value of the slope. So because the slope is 0, I look off the graph. This shows that it's 0 to both sides, and you've graphed it. I know it's a challenge. It says for 19 and 20, use the graphs of the derivative above to sketch a possible graph of f. So for 15 and 16. So let's look at this again. So at 15, we already did this part. So that's concavity. And then if I did the first derivative one for 15, it has no x-intercepts, but it does at 0 is undefined. But now I'm looking for increasing. I'm looking for above or below, right? So both are above on both sides. So what could be a possible graph of this? So it's going to be an asymptote. And so what I'm looking for here for the second derivative and the first derivative. So it's concave up and increasing. So concave up and increasing. This one means it is concave down and increasing. Concave down, but increasing. So that's a possible graph of what it could look like. So concave up and increasing, concave down and increasing, and it matters that this picture matches these number lines. Number 16, sorry, this is 19 and 20. So this is number 19, this is number 20. So for number 20, I look back at 16, and the second derivative at 2 was concave up through everything. And then if I look at the first derivative, let's see what the x-intercepts are for number 16. So I see one at -2. Actually goes -2 to 5. So at -2. And then we have a x-intercept at +2. Actually, it's at +3. So 2 and 3. It's really just 3. And so it is above, and then from 2 to 3, actually 2 is on here because it's undefined. So from 2 to 3, it's below, and then from 3 on, it's above. So positive, negative, positive. So those are the numbers I'm looking at. So when I graph this from -2 to 5, 2, 3, 4, 5. So first of all, it just has to match this. So it's going to smile and go up. And then it's going to, and that goes to what number? To 2, right? So smile and go up to 2. So smile and go up to 2. And then from 2 to 3, it's going to decrease, again smiling. So there could be a hole right there, but you can see if it smiles in both ways, it creates a cusp, and the derivative would be undefined. That's for 3. And then after 3, it's going to be concave up and go up. And that's it. And again, does it match? Like concave up and increasing. At between 2 and 3, is it decreasing but still concave up? And then after that, is it increasing again? So at 3 creates a minimum, right? A turning point. And at 2, 3, it also creates a maximum, a local minimum. These are challenging questions, right? So we're going to do our best to keep practicing and not give up as we try to understand it. But at least we have each other, right, to go through it. All right, 21. It says 21. It says use the graph of the first derivative to sketch a graph of f. So I need that one for what just happened. So for 21, I need 17. So for 17, this is what we had. We had -2, 0, 2. This is negative, positive, negative, positive. That's the second derivative. If I would do the first derivative looking off of 17, I'm just looking at the x-intercept, -2, the other x-intercept, +2, and everything is above. So the whole thing is increasing. So if I want to and I have a starting point here. And my starting point is at -2, -2. So at -2, -2, I have a starting point. The whole thing is going up, but it's either going to frown or smile. So first of all, it frowns. So first of all, it frowns, and then it's going to smile up to 0. Frown, smile, and then it's going to frown up to 2, and then after 2 it's going to smile again. So at each interval it's increasing throughout, and it frowns, smile, frown, smile. So we're following the concavity and realizing the whole thing is increasing. 22. So for this one, the second derivative, just at 0, it had no concavity. So for 20, it had no concavity. Both sides had a slope of 0, but it had no concavity. If I look at the first derivative there for it, just at 0, it's undefined. And this one you look above and below. So here it's above, here it's below when I look at question number 18. And now I need to put that together. So at 0, it could be a hole or it could be something else, but I do know there's no concavity. So with no concavity, it's going to be a slope line, and it's going to be increasing and then decreasing. Done. And these have the slopes of 2 and -2, so this goes up. So this one would be like up 2 over 1 kind of thing. This would be down 2 and over 1. So looking off the graph, the +2 tells me the slope of this is +2, so it's a little skinnier, and -2 than that. But you can tell it increases, decreasing, and then the derivative doesn't exist, and there's no concavity when they're lines. All right, 23. Off of that. That was tough. Can you take derivatives? So for 23, I'm going to write this calculus friendly right away. This is the product rule. So that's the first times the derivative of the second. And there's a little hook for the second one. So the first times the 1/2 in front. 1 take away 2 is -1/2. And then the derivative of the base is the hook plus the second times the derivative of the first. The derivative of x is 1. I don't need it. It's over. 24. Can you take the derivative implicitly? So x's and y's are together here. It's not y equals, so it's going to be 2x. This is the product rule, which is the first times the derivative of the second plus the second times the derivative of the first. Y is y prime, and the derivative of 8 is 0. If it has a y prime, it stays. Otherwise, oops, that's a y prime. So we're going to subtract 2x, add 2y, factor out y prime, and then divide. So we get -2x plus 2y divided by -2x plus 1. $25. Can you do the quotient rule? So for 25, the quotient rule is the bottom times the derivative of the top, subtract the top, times the derivative of the bottom, and then the bottom squared. That's it. I don't want to simplify it. $26. Find a point tangent. That means derivative. So I'm going to take the derivative of f at x, 6x minus 2. Parallel means the same slope. So the slope of that line that I see is 10. So parallel means the same slope. The slope is 10. Take the derivative equal to 10. Add 2, divide, and it says the point. So x is 1. To find the y coordinate, then you plug it back in to the function. So if you plug 2 back in, it would be 3 times 2 squared, 2 times 2 plus 5. So if you plug 2 back in, you get 12, take away 4, plus 5, I get 13. So 2 and 13. Sure that one's right. There you go. And now the last question, 27, to do with velocity, placement, and acceleration. So the position of an object moving horizontally is s of t equals t 2t cubed. Subtract 3t squared minus t plus 8. All right, so now let's answer some questions. What's the velocity equation? The derivative. It says, what's the initial velocity? That's when you plug in 0, and you get 0, and it's centimeters per second. Right? Did I forget one? Oh, negative t is -1. So when you plug it in, you get -1. And 8 is 0. All right. Part C. What's the acceleration? So that's the derivative of the velocity. So that's 12t minus 6. What's the acceleration at 3? So plug 3 in, and you get 36, take away 6. I think it's 30, and that's centimeters per second squared for acceleration. Part E says, what's the object's speed at 1 second? So that's the absolute value of velocity. So if you plugged in 1, you would get -1, but the absolute value of that would be 1 centimeter per second, because it's the absolute value of that. F, it says, when is the object moving left? So we're going to have a velocity. We take the velocity equal to 0 and solve it. So if you make that equal to 0 and you solve it, I'd use a calculator. So if you took this and you used a calculator to solve it, oops. So if you took this, let's do that, show you. So press menu, then algebra, then factor, or solve, I should say. And then we have 6t squared, subtract 6t, subtract 1, comma t, oops, equals 0. You can see it is, oh, my screen here, the lighting of it. Anyway, it's irrational. That's why I said for you to do it that way. So it's 0.14, here it is right here. Oop. So one's negative 0.145. And the other one's 1.145. So there's your, so it wasn't factorable, that's why I said use your calculator. This is the velocity. Plug in a number that's super negative, and the answer will end up being positive. Plug in 0, and you get a negative answer. Plug in a super big positive number, and you get positive. So it's positive, negative, positive. The question was for F, when is it moving left? So from 0.145 to 1.5, and then positive 1.145. It is moving left because the velocity is negative. Part G. So in part G, what is the object's displacement? So for the displacement, we just take the end and the beginning. So this is between 0 and 2 seconds. So plug in 2, plug in 0, and you get the answer 2, and it's in centimeters. What's the total distance traveled? So between 0 and 2, we do have it changing directions here. So for total distance, I got to use 1.145. And the absolute value of that. And then I got to use 1.145. Plug this, using your calculator, plug this into this up here. So this is what you would plug into to get your answer. So 1.145 and take away that. So the first part would give you the answer so it's this up here is 8. Here is 5.924. This is 5.924. Oops, sorry. At 2, what is it, 10? So it's 10, take away 5.924. Add those two up. So 8 take away, 10 take away, add that up, and you get 6.151. So the numbers are super awkward, but the concept I definitely want you to feel very confident in. That if I want to know total distance, I need to know when the object changed directions. If it changed directions in my interval, that then I have to set up each situation, left and right, absolute value, and then find the distance that way. I and J, here we go. When is the object's velocity decreasing? So for velocity decreasing, that is the acceleration. So I'm going to make it equal to 0. I'm going to solve it. So add 6, divide. So at 1/2, the acceleration is 0. So if I try on both sides, if I plug in like 0, you get a negative answer. Here you get a positive answer. So when is it decreasing? So it's decreasing from negative half, or negative infinity to 1/2. This velocity shows it decreasing. And then the last question is, when is the speed decreasing? So for the speed decreasing part, I need to look at both signs of the velocity and the acceleration. So for the velocity, I had negative 0.145 and 1.145, and it went positive, negative, positive. And then for the acceleration, it was just 1/2, and it was negative, positive. And I'm going to line them up. 1/2 is 0.5. The speed is decreasing when the signs are different. So the first is positive, negative, the signs are different. So from negative infinity to negative 1.145, the signs are different. One's positive and one's negative. Where else are the signs different is from right here, from negative and positive after 0.5. So from 0.5 to 1.145, one's negative and one is positive. For the other one, one's positive and one's negative. So again, the numbers are super awkward, but the concept of whether speed is increasing or decreasing has to do with both velocity and acceleration. So if the signs are the same for velocity and acceleration, it's speeding up, whatever direction it's going. If the signs are different, it's slowing down no matter what direction it's going. So we're looking for where the signs were not the same, and we put those intervals down. When we're looking at velocity increasing or decreasing, we're just looking at acceleration and whether it's positive or negative. So I only needed to look at acceleration for this one, but for this one, I needed to look at both. So super challenging review. I'm glad we got to do it together, and I'm glad you didn't give up. And often, as we work through these, later on as we review, some of this will become easier and easier to do when you don't give up and keep working with me. So I'm proud of you that you got to the end of this. Mr. G Math over and out. Until next time.